Okay, today we have Kepler's laws of planetary motion that we're going to go over, and we're going to jump right into it. So the first one is, well, his first law. The first law of planetary motion is planets move in elliptical orbits. Planets move in elliptical orbits with the sun or any other star as a focus. Now, we say the sun or the star. This could also be the Earth as opposed to like the moon, but this is the basic idea of it. And because it's an elliptical orbit, this is how we make an ellipse. And I've tried to do this, and it hasn't quite turned out as happy as I wanted. But the idea is, the official definition of an ellipse is the locus of all points where the sum of the distances from the sum of its distances from two other points is a constant. I've got something rolling away from here. Okay, so we're going to attempt this on my paper here. I hope we have success with this. I tried this out and I found that to really get a good ellipse, I've got to stretch this out a little bit. Okay, now this is going to... Alright, so we have that, and then to make our ellipse, we stretch this out, and here's my point. And we circle it around. Okay, and here's... Now, you may see, there we go. Okay, so there's our ellipse, and it is the sum of the distances between 2 points is a constant. So that means that that the lines of the string that I'm drawing are always going to be a constant length from these two. Now I've created here a very eccentric ellipse. But the idea is that one of these would be the sun. So this would be the sun, and the planet would go way out and come back in. This is for a very elliptical orbit. Interestingly, Pluto has a very elliptical orbit, and that's why from time to time during its path around the sun, there's a stretch where Neptune is the furthest planet from the sun, and other times when, but most of the time Pluto is the furthest planet from the sun. So that's why we say Pluto's the ninth planet, or planetoid, or whatever. It's the furthest thing out there. Okay, so let's do that. Okay, so let's draw our ellipse here, and I'm going to make it more. Oh, that's horrible. More eccentric than the actual orbit. So this would be one focus, and let's say this was the sun. Okay, here's our sun. All right, so that's the first law, is that planets move in elliptical orbits with the sun as a focus. All right, the second law. The second law is that a planet will sweep out equal areas in equal times. Okay, so what exactly does this mean? Well, here's what we're saying about this, that as a planet is close to the sun, okay, as it moves from R1 to R2, and it takes a certain amount of time. There's a delta t, we'll call this delta t1 right here. that this area, the area of this arc, subtended with it, you know, from the center out to the circle, the area that is subtended by this arc, is equal to, oh, sorry, wrong focus, is equal to this area, which I probably did not draw it correctly, not nearly to scale, to this area where this is R3 and R4, but the time that it takes to go from here is delta T1, that these two are the same amounts of times, that this A is going to equal this area. So that this area drawn out by this arc sweeping out is equal to this area over here. And what this means is that the planet, as it's going around the sun, will go out and go really slow, and then it'll speed in, and then it'll go back out. And so this time right here, I really made this way too wide line. In fact, I think I'm going to reset that and do it in a different color here, just to give you a better idea. That it should really be something like,
Jeff Williams, please call the switchboard. Jeff Williams, please call the switchboard.
It should really be something like that. Okay, for a delta t. So let's forget about this other area up here. This doesn't exist, and we have this right here. That's going to be our delta area. Well, what governs this? Okay, so let's look at what's actually happening on a planet that's traveling around. So we have, here's our planet, and this is experiencing a force at any given moment that is directed right at the center of, or right at the center mass of the other gravitational object, which would be the sun right here. Okay, and so that's the force vector, and it's right along the r vector. Okay, and so the torque on this object, all right, the torque on this object equals r cross f. Okay, but in r cross f, now we also the r cross f is rf sine of 180, because these two are pointing in opposite directions. But sine of 180 equals 0. So that means our torque equals 0. What is that going to tell us about our change in momentum? Okay, what happens here? What happens to our change in our momentum? Well, if dl dt, okay, I'm sorry, if our torque equals 0, if we have no force or no rotational force acting on an object, then our rotational momentum, okay, must be conserved. Okay, or it equals a constant, therefore it is conserved. All right, now if it's conserved, that means L equals R cross P. Okay, and so we're going to draw this again. I hope they'll draw it better than last time. It's a little better. All right, so our R cross P, as we sweep out from, we're going to go from here to here. So that's an R. Okay, now our momentum, this is a mass right here, and our momentum is taking us this way, not quite directly on this line. Okay, but we do have, if this is really, really small, if this becomes a slight change, that the arc length actually equals dr, particularly if we're doing this in radians. So for a very small change, this arc length here equals dr. Okay, and so it's time we do a little bit of we need to do a little bit of vector review here. So what does it mean if we have A crossed with B? Okay, what does this concept mean? Well, if we have a vector A and we have a vector B, vector A and vector B. Okay, the magnitude of this, the magnitude of A cross B, okay, is going to equal, well, we know already this is A, B sine theta, if that's theta right there. But what is, how can we interpret that in graphic form? Well, we do this. And what happens if we draw new versions of A and B, and here's A, and here's B, a ghost B. All right, what is this area? Well, how do you find the area of a parallelogram? Well, we do base times height, right? So the length of this base times the height of this. But if this is theta right here, what's the height over here going to be? This is going to be the sine of theta with B. Okay, so it's going to be A. So this right here is B sine theta. And so the area of this equals A times B times sine theta. So what we're actually finding is when we do the magnitude of the new vector, it's actually the area of the parallelogram that we draw with these two vectors. So what does that tell us? Okay, that's getting us back into the idea of our area. So let's go back to R cross P. R cross P, okay, really equals R times, well, the momentum of P is going to be the mass, and our mass shouldn't be changing, times our velocity. And this equals R cross M dr dt, because this is the instantaneous rate of change of its position, which is what velocity is. Okay, which means that which now means that we have now this R times dr is really equal to 2 times dA. Okay, or in other words, R, we're really looking for a really tiny triangle here, right? Okay, and so 1/2 base times height, okay, is equal to the area of this triangle. Or if we multiply the 2 over, then 2 times the area of the triangle is equal to R cross dr. That's how we get this 2 dA here. It's this double triangle here. So dA dt, and area is still a vector, equals R cross dr over 2 dt. Okay, and both of these have mass over mass. Okay, well, okay, this gives us this can give us, we're going to take a little liberty here. We're going to multiply this by mass over mass. And we multiply by mass over mass, we get R cross M dr dt over 2m. This becomes R times mv over 2m. And what's R times mv? This is equal to our angular momentum over 2m. And because there's no torque, okay, L is constant. Okay. And 2m is constant. So dA over dt is a constant. Or the rate at which area is swept out per unit time is a constant as we travel around the ellipse. Okay? It took Kepler 20 years to prove what we just did in in about 15 minutes. Why? Because we have calculus. Okay? And we know about things like momentum and torque. And because we have all of these things, we were able to prove what it took Kepler 20 years to prove. Because he did it the hard way. Okay? And this finally brings us to Kepler's third law. All right. Kepler's third law is simply stated: the period of rotation, the square of the period of rotation is proportional to the length of the semi-major axis cubed. Okay, the semi-major axis is the long way. It's this distance from here all the way to here through both of the foci. Okay, that is the length of the semi-major axis. Now t equals the period of rotation. Okay, in time. Okay, in seconds. And a, like I said, is length of the semi-major. Length of the semi-major axis. Okay. Now, if we take our ellipse here and we pull our foci, so let's take this ellipse here, and if we were able to drag these foci together and put them overlap so that the two foci overlap each other, what happens to that ellipse? Okay, yeah, it becomes a circle. So we are going to do this in terms of a circle, which is pretty much how all of the planets, except for Mars. Mars has a visibly eccentric orbit, but Earth, okay, it does not. It's very close to a circular orbit. So in this case, when there's one foci, okay, A is equal to R. So we're going to start using R for this. So we have our circular planet. In fact, I'm going to. I'm running out of room on here, so we're going to move on. Okay, that we have our circular. Now that's a pretty darn good circle right there. Okay, we have a massive object in the middle. Okay, we have a smaller mass on the outside. Okay, we have a radius of the circle. Okay, and the question here is, how long does it take for, say, the Earth to travel around the Sun? Well, 1 year. Okay, but what would it take for anything traveling a particular velocity to travel around its circumference? Well, the velocity, the linear velocity this is going to be, the amount of time is going to be on the bottom, how long it takes to do this, and on top is going to be our circumference, which is 2 pi r. And so, okay, and this t is no longer just t, it is now capital T, because this capital T stands for the period of rotation, and every t seconds you're going to be going around the circle 2 pi r times. That's by definition what t is. Okay, so we're going to have this off to the side. Now, we know that the force of gravity acting on this object, okay, is equal to g times the big mass times the little mass divided by r squared. But since this is the only force acting on the object, okay, and it's centripetal, therefore there's no torque. Okay, this is the centripetal force. This is the force causing it to travel in a circle. So this also equals the little mass. It's the force acting on this thing. So it's the little mass times its acceleration, which is going to be v squared over r to the first. To make sure that's make sure it's just a 1. Don't get it. We have a lot of squareds going in there, so make sure we're keeping this as r without a square on it. So what do we have here? Where force of gravity here equals our centripetal force. Well, we can get rid of the masses on both of these. We don't need those. We can figure out where we're going to from there. And our velocity is this guy up here. So we have gm over r squared is equal to, and we're going to square this whole thing, so it's going to be 4 pi squared r squared over t squared r. Well, one of these r's is going to cancel with that r. Okay, and if we want to solve for t squared, all of us, so we're going to get t squared by itself. We're going to multiply t over here and flip it around. We're going to get t squared equals 4 pi r cubed over gm, or if we write it again, t squared t squared equals 4 pi squared over gm, and that is a constant times r cubed, and there we have it, that our t squared is proportional to our r cubed. And this is how we solve for the mass of extrasolar bodies. So we can figure out how far they are away from their sun. So like extra planets, from planets that are way out there, we can determine how long it takes for them to go around their star. We can measure how far away from their star they are. Well, 4 pi squared and g, those are all pretty fundamental constants, and that's how we find out the mass of that thing, and whether we know it's going to be a Goldilocks planet or something that's way too small, or all sorts of things. But this is the idea. This mass being so small is why why comets and things have such a huge period of orbit usually, because the mass is really small, which makes the radius huge, which also makes the time really big. So those are Kepler's third laws, and check this out on Edmodo, and we'll see you guys tomorrow.